Good day. The theme of our today's class, the first topic, the limit of a ratio of two infinitesimals, evaluation of indeterminate form of the type 0/0. Take your copybooks, take your pens or pencil and write down our topic. The limit of a ratio of two infinitesimals evaluation of indeterminate form of the type 0/0. Let the functions f of x and phi of x on a certain interval from a to b satisfy the Cauchy theorem and vanish at the point x is a of this interval. F of a equals 0 and phi of a equals 0 too. The ratio f of x over phi of x is not defined for x is a. But has a very definite meaning for the values x not equal to a. Hence, we can raise the question of searching for the limit of this ratio as x approaches a. Evaluating limits of this type is usually known as evaluating indeterminate form of the type 0/0. We have already encountered such problems, for instance, when considering the limit as x approaches 0, sine of x over x. And when finding derivatives of elementary function. For x is 0, the expression sine of x over x is meaningless. The function f of x is sine of x over x is not defined for x is 0. But we have seen that the limit of the expression sine of x over x as x approaches 0 exists and is equal to unity. Write down L'Hopital's theorems. Oh. Let the functions f of x and phi of x in some interval satisfies the Cauchy theorem and vanish at some point x is a. F of a equals phi of a equals 0. Then if the ratio f prime of x over phi prime of x has a limit as x approaches a, there also exists limit as x approaches a f of x over phi of x, and this limit equals to limit as x approaches a, f prime of x over phi prime of x. Proof. On the interval from alpha to beta, take some point x don't equal to alpha, Applying the Cauchy formula, we have f of x minus f of a over phi of x minus phi of a is f prime of c over phi prime of c, where c lies between a and x. And if limit as x approaches a, f prime of x over phi prime of x equals a capital A, then limit as c approaches a, f prime of c over phi prime of c exists and is equal to a. Whence it is clear that limit as x approaches a, f of x over phi of x is equal to limit as c approaches a, f prime of c over phi prime of c equals limit as x approaches a, f prime of x over phi prime of x and equal to capital A. And finally, limit as x approaches a, f of x over phi of x equals limit as x approaches a, f prime of x over phi prime of x. Note 1. The theorem holds also for the case when the function f of x or phi of x are not defined for x is a, but their limits as x approaches a exist and equal to 0. In order to reduce this case to the earlier considered case, we redefine the functions f of x and phi of x at the point x is a so that they become continuous at the point a. To do this, it is sufficient to put f of a is limit as x approaches a, f of x is 0, and phi of a is limit as x approaches a, phi of x is 0 too. Since it is obvious that the limit of the ratio f of x over phi of x as x approaches a does not depend on whether the function f of x and phi of x are defined at x is a. Note 2. The theorem holds also if f prime of a is phi prime of a is 0. If f prime of a is phi prime of a is 0, and the derivatives f prime of x and phi prime of x satisfy the conditions that were imposed by the theorem of the functions f of x and phi of x, then applying the L'Hopital rule to the ratio f of f prime of x over phi prime of x, we arrive at the formula limit as x approaches a, f prime of x over phi prime of x equals limit as x approaches a, f 2 prime of x over phi 2 prime of x, and so forth. Consider the example. Example 1. Find limit as x approaches 0 sine of 5x over 3x. We have indeterminate form 0 over 0 because our numerator sine of 5x as x approaches 0 approaches 0 too, and 3x approaches 0. And we can use the rule of L'Hopital. Find limit as x approaches 0, derivative of numerator over derivative of denominator. We have limit as x approaches 0, derivative of sine of 5x is 5 cosine of 5x. Derivative of 3x is 3, and our limit will be 5 over 3. Example 2. Find limit as x approaches 0, natural logarithm of 1 plus x over x. We have again 0 over 0. Yeah, so cool. And use the rule of L'Hopital. Derivative of numerator over derivative of denominator. We know that derivative of natural logarithm is 1 over argument. Derivative of argument in our case is equal to 1. Derivative of x is 1, and we have 1 over 1 plus 0 over 1. It is 1. Next example, example 3. We find the limit as x approaches 0, e to the power of x minus e to the power of minus x minus 2x over x minus sine of x. We have indeterminate form 0 over 0, and we can use the rule of L'Hopital. Define limit as x approaches 0 ratio of derivatives numerator and denominator. Calculate these derivatives. And we have again 0 over 0, because e to the power 0 is 1, e to the power minus 0, 1, 2, 1 plus 1 minus 2 is 0, cosine of 0 is 1, 1 minus 1 is 0, 2. If 0 over 0, we can use the rule of L'Hopital. calculate e to the power x minus e to the power minus x, derivative of constant is 0, here 2 sine of x. And we have 0 over 0 again. Use the rule of L'Hopital. And in the end, we can calculate it e to the power 0 plus e to the power minus 0, it is 2, 1 plus 1, over cosine of 0, over 1. It is 2. Here, we had to apply the L'Hopital rule 3 times, because the ratio of the first and second derivatives at x is 0 yield the indeterminate form 0 over 0. Note 3. The L'Hopital rule is also applicable if limit as x approaches infinity f of x is 0 and limit as x approaches infinity phi of x is 0 too. Indeed, putting x is 1 over z, we see that z approaches 0 as x approaches infinity. And therefore, limit as z approaches 0, f of 1 over z is 0, and limit as z approaches 0, phi of 1 over z is 0 too. Applying the L'Hopital rule to the ratio f of 1 over z and phi of 1 over z, we find limit as x approaches infinity, f of x over phi of x equals limit as z approaches 0, f of 1 over z over f phi of 1 over z, or limit as z approaches 0, f prime of 1 over z we must multiply by derivative of argument of our function. It means 1 over z, derivative of 1 over z is minus 1 over z squared. Over same way, pi prime of y over z times minus 1 over z squared equals limit as z approaches 0, f prime of 1 over z over phi prime of 1 over z, or limit as x approaches infinity, f prime of x over phi prime of x, which is what we wanted to prove. Example 4. Find limit as x approaches infinity sine of k over x over 1 over x. It equals limit as x approaches infinity. We have in this indeterminate form 0 over 0. K times cosine of k over x times minus 1 over x squared over minus 1 over x squared, cancel minus 1 over x squared out, and we have k times cosine of 0 or just k. Next topic, the limit of a ratio of two infinitely large quantities evaluation of indeterminate form of that type infinity over infinity. Let us now consider the equation of limit of a ratio of two functions f of x and phi of x approaching infinity as x approaches a or as x approaches infinity. Theorem. Let the functions f of x and phi of x be continuous and differentiable for all x not equal to a. In the neighborhood of the point A. The derivative f prime of x does not vanish. Further, let limit as x approaches a, f of x is equal to infinity. Limit as x approaches a, phi of x is equal to infinity. And let there be a limit limit as x approaches a, f of x over phi of x, f prime of x over phi prime of x equals a capital A, expression 1. Then there is a limit As x approaches a, f of x over phi of x and this limit is equal to limit as x approaches a, f prime of x over phi prime of x and equals a capital A. Expression 2. Proof. In the given neighborhood of the point A, take 2 points A and x, alpha and x, such that alpha is less than x and x is less than A, or A is greater than x is greater than alpha. By Cauchy's theorem, we have f of x minus f of alpha over phi of x minus phi of alpha equals f prime of c over phi prime of c. Expression 3, where c between alpha and x. We transform the left side of expression 3 as follows. F of x minus f of alpha over phi of x minus phi of alpha equals f of x over phi of x times ratio of 1 minus f of alpha over f of x and 1 minus phi of alpha over phi of x. Expression 4. From relation 3 and 4, we have f prime of c over phi prime of c equals f of x over phi of x times 1 minus f of alpha over f of x over 1 minus phi of alpha over phi of x. Whence we find f of x over phi of x equals f prime of c over phi prime of c times 1 minus phi of alpha over phi of x over 1 minus f of alpha over f of x. Expression 5. From the condition 1, this condition, it follows that for n arbitrary small epsilon is greater than 0, alpha may be chosen so close to A that for all x is C, where C between alpha and A, the following inequality will be fulfilled. F prime of C over phi prime of C minus capital A is less than epsilon, or capital A minus epsilon is less than f prime of C over phi prime of C is less than capital L plus epsilon. 6. Let us further consider the fraction 1 minus phi of alpha over phi of x over 1 minus f of alpha over f of x. Fixing alpha as in such manner that the inequality 6 will be fulfilled, we allow x to approach A. Since f of x approaches infinity and phi of x approaches infinity as x approaches A, we have limit as x approaches A of 1 minus phi of alpha over phi of x over 1 minus f of alpha over f of x equals 1, because phi of x approaches infinity, phi of alpha over phi of x approaches 0, and same way with f of alpha and over f of x. And consequently, for earlier chosen epsilon is greater than 0 for x sufficiently close to alpha, we will have modulus 1 minus this ratio is less than epsilon. Or 1 minus epsilon is less than 1 minus phi of alpha over phi of x over 1 minus f of alpha over f of x is less than 1 plus epsilon. Expression 7. Multiplying together the appropriate terms of inequalities 6 and 7, 6 it is this, and 7 it is this. We get a minus epsilon times 1 minus epsilon is less than f prime of c over phi prime of c times our ratio and less than a plus epsilon times 1 plus epsilon. Or from 5, expression 5, this, a minus epsilon times 1 minus epsilon is less than f of x over phi of x is less than a plus epsilon times 1 plus epsilon. Since epsilon is an arbitrary small number for x sufficiently close to a, it follows from the latter inequalities that limit as x approaches a, f of x over phi of x equals a. Or by 1, this 1, limit as x approaches a, f of x over phi of x equals limit as x approaches a, f prime of x over phi prime of x equals capital A, which is what had to be proved. Note 1. If in premise 1 this expression 1 alpha equals infinity, that is limit as x approaches a, f prime of x over phi prime of x equals infinity, then equality 2 holds. Equality 2, it is this equality. Equality 2 holds in this case as well. Indeed, from the preceding expression it follows that limit as x approaches a phi prime of x over f prime of x is equal to 0, then by the theorem just proved, limit as x approaches a phi of x over f of x equals limit as x approaches a phi prime of x over f prime of x equals 0. Whence limit as x approaches a f of x over phi of x is infinity. Note second. Note 2. The theorem just proved is readily extended to the case where x approaches infinity if limit as x approaches infinity of f of x equals infinity and limit as x approaches infinity phi of x equals infinity and limit as x approaches infinity f prime of x over phi prime of x exists, then limit as x approaches infinity f of x over phi of x will be equal to limit as x approaches infinity f prime of x over phi prime of x, the expression 8. The proof is performed by replacing x is 1 over z as was done under similar condition in the case of the indeterminate form 0 over 0. Consider the example. Example 1. Find limit as x approaches infinity e to the power of x over x. We have indeterminate form infinity over infinity. Using rule of L'Hopital, we have limit as x approaches infinity e to the power x prime over x prime, or limit as x approaches infinity e to the power x over 1 or infinity. Note 3. Once again, note that formulas 2 and 8, this formula 2 and this formula 8, hold only if the limit on the right, finite or infinite, exists. It may happen that the limit on the left exists, while there is no limit on the right. To illustrate, let it be recurred to find limit as x approaches infinity, x plus sine of x over x. This limit exists and is equal to 1. Indeed, limit as x approaches infinity, x plus sine of x over x equal to limit as x approaches infinity, 1 plus bounded function sine of sine of x over the function approaches infinity x, bounded function over infinity approaches 0, and we have 1. By the ratio of derivatives x plus sine of x and x equals 1 plus cosine of x equals 1, or just 1 plus cosine of x. As x approaches infinity, does not approach any limit, is oscillated between 0 and 2. Example 2. Find limit as x approaches infinity, ax squared plus b over cx squared minus d, or it is indeterminate form of infinity over infinity. Use the rule by L'Hopital. We have limit as x approaches infinity. Derivative of ax squared plus 2 will be 2ax. Derivative of cx squared minus d, 2cx. And we have just a over c, because we can cancel 2x out in our ratio. Example 3. Find limit as x approaches pi over 2, tangent of x over tangent of 3x. It is tangent of pi over 2 approaches plus infinity. Tangent of 3 pi over 2 approaches minus infinity. And we have infinity over infinity, and we can use the rule of L'Hopital. Find the derivatives of numerator and denominator. Derivative of tangent of x is 1 over cosine squared of x. Derivative of tangent of 3x is 3 over cosine squared of 3x. Or it will be limit as x approaches pi over 2, 1 over 3 times cosine squared of 3x over cosine squared of x equals here we have infinity over infinity again. And use the rule of L'Hopital again. We have 2 times 3 times cosine of 3x times here 3 times sine of 3x over 2 cosine of x times sine of x, or product of limit as x approaches pi over 2 cosine of 3x times cosine of x and limit as x approaches pi over 2 sine of 3x over sine of x. The first limit has the indeterminate form infinity over infinity. The second limit, calculate. We have, using the rule of L'Hopital again, 3 minus 3 sine of 3x over sine of x in the first integral. In the second integral we have minus 1 over 1. And here we have 3 times minus 1 over 1 times minus 1, but just 3. Example 4. Limit as x approaches infinity x times e to the power of x. Infinity over infinity. Use the rule of L'Hopital. Derivative of x is 1, derivative of e to the power of x is e to the power of x, 1 over infinity is 0. Generally for any integral n greater than 0, limit as x approaches infinity x to the power of n over e to the power of x will be 0 too, because nth derivative of x to the power of n will be n factorial, derivative of e to the power of x n times will be e to the power of x, because derivative of e is e, and we have constant over infinity or just 0. The order indeterminate forms reduce to the foregoing cases. Their forms may be written symbolically as form a 0 times infinity, b 0 to the power of 0, c infinity to the power of 0, d 1 to the power of infinity, and e infinity minus infinity. They have the following meaning. Consider the case A, 0 times infinity. Let limit as x approaches a, f of x is 0, and limit as x approaches a, phi of x is infinity. It is required to find limit as x approaches a, f of x times phi of x. This indeterminate form is of the type 0 times infinity, this type. If the required expression is rewritten as follows, limit as x approaches a, f of x times phi of x is equal to limit as x approaches a, f of x over 1 over phi of x, then x approaches a, we obtain the indeterminate form 0 over 0. And we can use the rule of L'Hopital. Or we can rewrite it in the form phi of x over 1 over f of x. Sorry, not very good. F of x, yes. And we have indeterminate form infinity over infinity. And we can use the rule of L'Hopital again. Example 5. Find limit as x approaches 0, x to the power of n times natural logarithm of x. Rewrite our limit as natural logarithm of x over 1 over x to the power of n. We have infinity or x to 0 over infinity. Use the rule of L'Hopital. We have limit as x approaches 0, derivative of natural logarithm is 1 over x, derivative of our denominator is minus n over x to the power of n plus 1, And if we there we have just minus limit Sx to the power of n over n, or just 0. Consider the case B. In the case B, we have 0 to the power of 0. Let limit Sx approaches a, f of x is 0, and limit Sx approaches a, phi of x is 0 too. It is required to find limit f of x to the power of phi of x as x approaches a. Or, as we say, to evaluate the indeterminate form 0 to the power of 0. Putting y is f of x to the power of phi of x. Take logarithms of both sides of the equality. We have natural logarithm of y is phi of x times natural logarithm of f of x. As x approaches a, we obtain on the right the indeterminate form 0 times infinity. Finding limit of natural logarithm of y, it is easy to get limit of y. Indeed, by virtue of the continuity of the logarithmic function, limit as x approaches a of natural logarithm of y is natural logarithm of limit as x approaches a of y. And if natural logarithm of limit of y is b, it is obvious that limit of y is e to the power of b. If in particular b is plus infinity or minus infinity, then we will have limit is plus infinity or 0 respectively. Example 6. It is required to find limit as x approaches 0, x to the power of x, 0 over 0. Putting y is x to the power of x, we find natural logarithm of limit as x approaches 0 of y is limit as x approaches 0 of natural logarithm of y, or limit as x approaches 0 of x times natural logarithm of x, or limit as x approaches 0, natural logarithm of x over 1 over x, or this we have infinity over infinity, use the rule of L'Hopital, we have limit as x approaches 0, derivative of natural logarithm of x is 1 over x, derivative of 1 over x minus 1 over x squared. If we calculate, we have minus limit as x approaches 0 of x, or just 0. Consequently, natural logarithm of limit as x approaches 0 of y is 0, whence limit of y as x approaches 0 is e to the power of 0 or 1, or limit as x approaches 0 of x to the power of x is 1. The technique is similar for finding limits in other cases. In this moment, our lecture comes to its end. I want to say you goodbye, good luck, and I disconnect.